In this video, I'm going to talk about spanning trees of graphs. So first, a reminder what a tree is. So a tree is a connected graph without cycles. So let's write it as a definition. So a tree is a connected graph without cycles. So now a spanning tree so let's say that we have a graph G. So a spanning tree of a given graph G of a given graph is a subgraph that is a tree and that contains all vertices. So a spanning tree of a graph. Well, we can write of a connected graph because it follows that it must be connected. Of a connected graph. Of a connected graph is a subgraph that is a tree and that contains all vertices of the original graph. So like if we denote it by G, all vertices of G. So we don't have to specify that it's defined only for connected graph, but it follows that it exists only for a connected graph because a tree is a connected graph, and if we have a subgraph that contains all vertices, then the original graph must be connected. So now the main theorem that I'm going to prove is that so let's write theorem that any connected graph has a spanning tree. Basically, simply the existence of the spanning tree. Any connected graph has a spanning tree. Okay, so let's draw some example. So we have, let's say that we have some graph. Let's say something like this. So what would be the spanning tree here? So we simply there are, like, by the way, it's not unique, but for example, we can take something like this. So this, 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 and this. So basically, we take all edges except this tree one that I didn't highlight. So this is like we directly see that it doesn't have cycles, and it contains all vertices of the original graph. So this is a spanning tree. Okay, so the proof is actually not that difficult. So basically all we need to do is to remove edges from the original graph until we can without violating the connectedness. So remove, so like we can do it in iteration. So at each iteration, like we construct, so we take first we take the, for this, so we construct the subgraph T. So and then we'll prove that at the final stage it will have the it will be a spanning tree. So we construct subgraph T of G, subgraph of G in iterations. Iterations. So first, so we start with the whole graph G. So we start with T equal to G, and at each iteration we remove an edge from T. We remove an edge from T without violating connectedness. Oh, let's write it differently. Not without violating connectedness, but let's say we remove an edge from T that belongs to a cycle, if there is any cycle. So if we remove an edge from T that belongs to a cycle, if any. So if there is any cycle in T remains, then we remove an arbitrary edge of this cycle. If there are no cycles, then this is a tree. So what we need to prove is that so first observe that we don't, so doing this we don't violate connectedness. So doing this, we don't violate connectedness of T. So if on the previous iteration T was connected, then on the next iteration it was also connected. Why is that? Well, because we remove only edges of cycles. So if we have a cycle, all we do is we remove, let's say, this edge. Then if there was a path previously between two vertices, U and V connectedness, it means that any two vertices can be connected by a path in the graph. So if this path doesn't pass through the removed edge, then nothing changes, like this path still exists. So the only case is when it did pass through this, the only case that we need to prove remains to prove is when it did pass through this edge. So path like this. Well, we can simply now go around this removed edge by the edges of the cycle. So the new path would go like this. And the U and V would still be connected. So the connectedness is not violated by this procedure. So at all iterations, T remains connected. Then we observe that these iterations, they cannot continue forever, because there is only a finite number of edges that we can remove. So the iterations cannot continue forever. Because at each stage, at each iteration, we reduce the number of edges in T by 1, and the number of edges cannot go negative. It's bounded from below greater than 0. So because the number of edges forever, because each iterations each iteration decreases the number of edges in T, and this number of edges, well, the number of edges, like, let's just we can denote it by so this is the decreases the number of edges in T, and this number of edges of T is of course bounded from below, so it's greater or equal than 0. So it cannot decrease forever. So at some point, it means that at some point the iterations would stop, and we could no longer so at some point, like after so this follows from this, after a finite number of steps, of iterations we could no longer continue. And the only way that we could no longer continue if there are no more cycles in the graph, because the iteration we defined like this. So at each iteration we remove an edge from T that belongs to a cycle, if any. So if there is any cycle in the graph. And this is the only way that we could not do an iteration if there is no longer any cycle. That's the only possibility. If there is a cycle, then we can do an iteration. So that means that at this point in this resulting graph, so at this point T has no cycles. If T has no cycles and it's connected because the iterations preserve connectedness, then T is a tree. So therefore at this point T would be a tree. Yeah, and it is a spanning tree because it contains all vertices, because we didn't remove any vertices. Our iterations consisted only on removing edges. We didn't change the vertices. So T is a tree and T is also a spanning tree. T is spanning tree. Yeah, so that concludes the proof. That's it.